All right, so I'm going to go over 5.5, number 9. This is the skier problem. Now, usually people only have trouble with part B. So I have part A on the board. I'm going to go over it really quick, but obviously I'm going to kind of go a little faster through that because I'm trying to get to part B. So on this, you're going down a ramp, the skier's going down a ramp, coming back up and leaving off of, sorry, down, I guess a slope more or less, leaving off of a ramp and flying through the air in 2D motion. Hey, that 2D motion doesn't exactly go away either. So we have conservation of mechanical energy. We assume there's no friction. If I did a force diagram here, you'd get force gravity down, force normal over, force friction. We're not assuming no friction. So yes, there's force normal, but it's not doing any work. So we have conservation of mechanical energy. I've set my 0 at the base. You could move your 0 so that you can cancel something, but it actually makes it a little bit harder here because you're dealing with multiple parts, both of which are using like different heights. I think the final answer of B is actually asking you for the height above the ground. So if you move the 0, you'd have to like remove it back to get to the ground. So I'm just going to leave it here at the ground. Conservation of mechanical energy. Again, I'm kind of ignoring elastic because it's not in this problem. Don't forget about it. It does in fact exist. We're going to see a bunch of problems with that, like the quiz that I'll actually do a video for here in just a minute. But we have gravitational, gravitational, and kinetic, initial, final. There is no kinetic initial because the person starts from rest, which it says in the problem. Definitely has gravitational. We see that height right there has gravitational at the end because of that height right there. Obviously, again, if you'd move the 0, that wouldn't be the case, but it's actually a little bit easier to leave it like that. And there's going to be kinetic at the end because it's definitely moving. So mass at every turn, those drop out. I subtract the GHI over, kind of did this all at once here, apply the 2 over, which you see around parentheses, and then square root the whole thing to get this guy here. You'll also notice as I move down here and plug my numbers in, I actually factored out the G even further, which you can leave in or factor out, which means obviously a little bit less numbers, and it's 2 times G times 40, which you'll notice would be the same if you had set that 0 there, and then that would just be your initial height of 40, same answer, you should get 28 meters per second. And here's where people struggle. The next question was, how high does the person get right there? And the major reason that they struggle is they forget our conversation from 2D kinematics. And that is simply this. The assumption that most people make is that the person is not moving there, which is not accurate. If they're in 2D motion, which this person definitely is, as you can see from the path, this person is moving strictly to the right. So we have to do a little bit of 2D stuff, but actually it's not really that bad because if you'll remember from 2D motion, if the only thing affecting the person is acceleration, then the velocity in the x stays constant. So if I just come right back down here to the beginning and I use the answer that I just have, I know that the person leaves at 28 meters per second. And so I just need to figure out how much of that is horizontal. So I'm going to do trig because I know that's 45 degrees. So the velocity in the x is 28 meters per second cosine of 45 degrees. So punch in the calculator. And we get 19.8 meters per second. So that, since it's only in the x here, and it's going to stay the same up there, that's how fast they're going at the top, 19.8 meters per second. So when we come back over here and we use this equation for part B, we're going to change where our initial and final are. Well, actually, quite frankly, we're just going to change where our final is. I don't know if you can see that's definitely a plus. Kind of looks like a negative in the camera there. Now, what do I mean by that? Well, even though we say initial and final, conservation of energy is true across the board. So if I have like 3 different spots, like let's call this guy spot A and this guy spot B, instead of saying initial and final, really this is mechanical energy at A is equal to the mechanical energy at B. That also means it's equal to the mechanical energy at C. Sometimes students feel like they have to move the initial to here. And the answer is you don't. You can because B is equal to C, but also A is equal to C. So let's kind of scrap the initial and final stuff for a second. which can be helpful when you have multiple spots, and say we're comparing the spots of A to the spots of C, because the energy is conserved. That number, whatever that was calculated at A, is still going to be the answer at C. Now, that means kinetic at A still drops out. Actually, this is, in fact, the exact equation again. Now, we're actually going to be solving for something different this time. But this is, in fact, the exact same equation, because there is gravitational up there, more so than there was here. And there is kinetic up there, less so than there was here. So let's erase the algebra off of that. And remember that we're trying to find essentially what is the height at C, which is right here. Oh, I didn't change those letters. It's A, that's C, and that's C. So let's subtract this guy over here. So we have G times height at A minus 1/2 velocity C squared is equal to G HC, and divide by G underneath. You'll notice obviously my mass has already canceled as it did in the first part. So 9.8 times the height of 50, right back up there, okay, minus 1/2 times the velocity at C, just 19.8, square that, enter, and divide by 9.8 again. And I get that the height is 29.9979, or 30. And that's how you do the skier problem.